Howdy, howdy, howdy! It's NEML time! Let's do some math. All right, we're doing NEML number 5. We are moving right along. We are in February. It is Valentine's Day, and it is just perfect time to do NEML. First problem from this past NEML. What is the sum of the reciprocals of the solutions of the equation x plus 1, x plus 2, x plus 3 equals 0? First thing to do, let's just find those solutions. You can actually just solve them in your calculator if you weren't sure, but hopefully you're all sure enough to know how to solve something in factored form. It's already factored for you, so you just say, when does x plus 1 equal 0? It equals 0 when x is negative 1. When does x plus 2 equal 0? It is when negative x equals negative 2 and x equals negative 3. Those are your 3 solutions. But again, if you're not 100% sure, plug it in your calculator. Your Inspire will do this for you. Now, we want the sum, which means add up the reciprocals. The reciprocals is 1 over those values. Plug that in your calculator, and there it is. 1 over negative 1 plus 1 over negative 2 plus 1 over negative 3 is negative 11 over 6. Boom. First one. Done. Second one. My thing is a little too big, I think. I gotta make it smaller. There we go. What is the largest integer n for which 2020 minus n, 2020, and 2020 plus n could be the length of the sides of a triangle? This is definitely asking you, do you know the triangle inequality theorem? Maybe you do, maybe you don't. But what it says is that the two sides of a triangle must always be greater than the longest side. So if A and B are the shortest sides, they must be greater than C. It has to be true, or else they won't reach. If A and B are 1 and C is 100, beep, 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 they won't reach each other. So they've got to be bigger. So clearly 2020 plus, since we want n to be the largest integer, 2020 plus n is going to be the largest side, because we want n to be the large positive integer, so that's going to be the longest side. So you can plug this into your calculator. Look at that! You can use the solve feature with inequalities. It's amazing. So you do 2020 minus n plus 2020. That has to be greater than 2020 plus n. For n, n's got to be less than 1010, less than, not equal to, less than. So 1010 does not work. That would just give you a line segment. So what's the largest value? 1009. Number 2 is done. Number 3, the only possible scores on an exam are the integers, are the 16 integers from 0 to 15. The most frequent score earned by the 100 students who took the exam was 0. That's unfortunate. That's not good. But a score achieved that's achieved by K students. We want to know if no other score was earned as frequently, what is the least possible value of K? So we want K to be small. So in order for K to be small, we want a good distribution of scores. So let's think about what's the maximum way we can distribute these scores. First off, if you have about 100 students and 16 possible scores, if we do 100 divided by 16, that's 6.25. So imagine putting 6 zeros, and then 6 people get a 1, 6 people get a 2, 6 people, all the way up to 6 people get a 15. If we do that, that's 16 times 6, that's 96 scores, all right, 96 students. We need 4 more students, so we got to plug in, we got to add more than a 6 4 times to different people. So if we do 4 are to the different scores. If we put 1 more at the 0, but then we do 1 more at the 1 and 1 more at the 2 and 1 more at the 3, for instance, that's not unique. You know, we still have 4 scores of 7. So in order to make a unique mode, is what we like to call it, you'd have something would have to score an 8. So the 0, there has to be 8 people that scored a 0, and then 2 can have scored a 7, and then all the rest 6 is one possibility. But you do have to have at least the least possible score would be an 8. I hope that makes sense. Next question, on to number 4 already. You got 2 isosceles triangles with supplementary vertex angles. So these are your vertex angles. They are supplementary, which means they add up to 180 degrees. They share this common base down here. Their legs are 12 and 5. All right. Now, when I first see this, it's a triangle, and they got the numbers 5 and 12. I immediately think of my Pythagorean triples, 5, 12, 13. I can't not think about that. So right off the bat, I'm like, 13. It's got to be 13. And I think some of you actually guessed 13 because you saw the 5 and 12. And you actually were correct. But let's do the math behind it. So I'm going to drop my altitude down, and if I drop this down, these two angles would be the same. They're both x. These two angles would both be y. And we know that 2x plus 2y, because they're supplementary, has to add up to 180. Divide everything by 2. That means x plus y would have to equal 90. So these two are complementary. Now, I'm going to break these triangles up for a second to notice something. So if this is 90 and if this is 90 here and this is x, these two angles also have to be complementary. So that means this would have to be y. Okay, this angle down here, so this entire angle over here is y. I take this little triangle over here, and since this is y and this is 90, these two would have to be complementary, so this little guy would have to be x. So I have two similar triangles here, if you notice. All the angles are the same. So I could create proportions, and I could solve for the two altitudes that way and add them together, and I would get my 13. It's a little bit messy, but you can do it. There's a little trick, though, which is beautiful. If I take this bottom triangle and I flip it to the other side, I get this shape here. All right, just half of the triangle though. I flip this little guy down here. There's my y, there's my x. All right, and we know that x plus y is 90, so this makes a right angle. There's my 5, 12, and I want the sum of these two. There's my 13. I've got it. I've got it. Oh, great problem. Love it. Love it. All right. On number 5, two numbers are called reverse numbers if one is obtained from the other by reversing the order of the digits, like 1, 2, 3, and 3, 2, 1. What are the two reversal numbers whose product is 92,565? So I'm going to take these two numbers, multiply them together, and get that. Notice it ends in a 5. So that means that one of my two numbers must end in a 5. There's no other way to get it. So I've got ABC and CBA. It's going to be a 3-digit times a 3-digit. You could play around with 2-digit numbers and 2-digit numbers, or 4-digit and 4-digit. You'll notice that they would be way too small or way too big. But 3-digit numbers are going to work, but they kind of hint at that. I feel like it's the problem too. But we know one of them has to be 5, so I'm going to put 5 in the C slot. So I have AB5 and 5BA, where B and A both represent digits. And now, since this has to be in the 500s, I can find out, instead of just trying to guess and check A and B, because there's a lot of possibilities for that, 90 actually. Instead of doing that, what I prefer to do is I'm going to plug in, I'm going to divide this number by 500. And if I divide it by 500 on my calculator, I get 185. So what that's telling me is like this is in the 100s. All right, so I'm going to plug in 1 for A, and suddenly I'm almost there. I've got 1B5 and 5B1. Now to solve for B, there's a couple different things I could do. I could notice that this is a multiple of 9. Therefore, these both have to be multiples of 3. And to be a multiple of 3, the digits all have to add up to be a multiple of 3. So if this is 5 and 1 and 6, therefore B would have to be 0, 3, 6, or 9. But again, doing that kind of math probably takes longer than just guessing and checking. There's only 10 possibilities, the digits 0 through 9 for B. It wouldn't take too long until you find the 165 and the 561 to get your answer. And you're done. There is another way that I kind of like even better. Let's take the prime factorization of 92,565. And if you do that, you get 3 squared times 5 times 11 squared times 17. All right. Now, if you're familiar with multiples of 3, as I said, like the 3 numbers, since this whole thing's a multiple of 9, and you notice right there, because you have the 3 squared, the 3 digits are going to have to each both be a multiple of 3. So basically, your 2 numbers, one of them is going to have a factor of 3, and the other one's going to also one of its factors will be 3, and the other one will also have a factor of 3. So I'm going to take the 3, and I'm going to split them up, split these 2 3s up. I'm going to basically build my 2 numbers out of these factors. So I've got the 3 squared. I'm going to put a 3 for one and a 3 for the other. 5 has to only go with one of the 2. I got my 11 squared, and that's another attribute of multiples of 11 is the way they, I mean, if you knew multiples of 11, how you add them up, you would have to notice that they would have to both be multiples of 11. Again, this was a little more advanced method, but I have to take the 11 and break it up. And then I'm just left with my 5 and my 17. So one of them gets the 5, one of them gets the 17. And so if I multiply 3, 5, and 11, I get 165, and 5, 11, 17, I get 561. So it's basically playing with the factors and reconstructing the numbers from their factors. But you have to know a little bit about multiples. But it's good stuff. I like it. All right, on to the last problem. What are all ordered pairs of non-zero integers a, b, c for which a, b, and c form a geometric sequence whose common ratio is a non-zero integer? Make sure you read that clearly. R can't just be any old fraction. It has to be a non-zero integer. And a plus 4, comma b, comma c form an arithmetic sequence. Let's do a quick review of what those two things even mean in case you're unfamiliar with them. A geometric sequence is a sequence of numbers where each term is found by multiplying the previous number by a common ratio, which you typically call R. So one example would be 1, 2, 4, 8, 16, 32. We're doubling it. We're multiplying by 2 every single time, so our R would be 2. Where an arithmetic sequence is a sequence of numbers where each term is found by adding the same number, which we typically call d to the previous term, like 5, 10, 15, 20, 25, 30. So our d in this case would be 5. So now let's go back to our problem. We have these 3 terms, a, b, and c. All right. Now to get from a to b, you have to multiply by some r value. So our geometric sequence, let me move this up a little bit. My geometric sequence, I would start with a, and then my next term would be a times r, and my next term would be a times r, ar squared. Now my arithmetic sequence, I start with a plus 4, all right, because that's what they tell me. I add some d to it, and I get to my b value, and I add some d to that, and I get to my c value. Now, what I could do is I could replace b with AR, because that's what b is according to my geometric sequence. I could replace c with AR squared, all right? And now I'm getting somewhere, because I know that a plus 4 plus d must equal AR. A plus 4 plus d equals AR. So I could solve this for d, just swing these guys to the other side, or subtract them really, don't swing them. And then over here, I know AR plus D has to equal AR squared. So AR plus D is AR squared. I can solve this for D, and I get AR squared minus AR by subtracting the AR over. So now I have 2 equations for D. I can set them equal to each other. And I'm just going to let the calculator simplify this for me. So I'm going to set these guys, these 2 are equal to each other, set them equal to each other, and solve in terms of A. A is my first term, R is my multiplier. They must both be integers, okay? Now notice something. I'm taking -4 and I'm dividing it by an integer squared. Any integer squared is going to give me a perfect square. And I want -4 over a number to equal a number, all right? The only thing I can divide -4 by that's a perfect square that will give me some kind of integer is going to be divided by 1 or divided by 4. Notice this can't be a negative down here because I'm squaring it. So r minus 1 squared has to either be 1 or 4. There's no other possibilities that will work. If it's larger than 4, a will be a fraction, all right? And so that's basically, that's a huge step right there. So r minus 1 squared has to equal 1 or 4. So if r minus 1 squared equals 1, I can solve this by basically, square rooting both sides. So r minus 1 has to equal 1. So r plus or minus 1. And so r either can be 0, because you plug in 0, 0 minus 1 squared is 1, or r equals 2. Now we already know r equals 0 does not work. They tell us that in the problem. Plus it wouldn't work anyway if you tried it out, because it would not work with the arithmetic one. But r equals 2, that's a possibility. So let's plug r2 in there. If we plug 2 in there, we get 2 minus 1 is 1. -4 over 1 is -4. So a would be -4. My r is my multiplier. I'm just doubling every time. So you take -4, double it. There's one of my solutions. Now let's go to the r minus 1 squared equals 4. And if you solve for this, you get two possible r's. Either r is -1 or r is 3. If r is -1, again, you plug that in there, you'd get 4 down here. -4 over 4 is -1, so a is -1. My r is -1, so I'm multiplying by -1, multiplying that by -1, so it just goes -1, 1, -1. And if you plug in 3 into this guy, a again would be -1, but your multiplier is 3, so -1, -3, -9, and those are my 3 solutions. We did it. We got them all. NEML number 5 is in the books. Hope you enjoyed it, and that's all I got for you until the next one. Have a good one.